Hi, everybody. Welcome to our first afternoon. Our first speaker this afternoon is Marcy Robertson. There's a very long time.
And I also have a kind of long abstract, and since there's a lot of young people in here, I'll say the last time I gave this talk, it was a 90-minute talk. And then I just reused the abstract, so it won't be that. All right, so I want to talk about, so luckily Mike set things up nicely and about little disc operads. And I want to talk about variations on these when you take linearizations or rational completions of little discs, how you arrive at interesting problems in algebra. And this starts with like kind of an old story. So I'm gonna write, I have to leave this configurations for the ordered configurations in the plane. So that just means my labels are, I'm keeping track of the label. And if I want to write the unordered configurations, I'm not sure what the standard notation is, but I wrote a bar for the orbits under the symmetric group actions for muting the label. And the thing I'm going to be interested in is that the fundamental groups, the fundamental group of the configuration, the unordered configuration space is the braid group. And I have that this has a preferred presentation, and the only thing that you need to know about this is that those are betas, because the symbol might appear elsewhere on the slide. So that's twisting one strand over another, or a half twist. And the pure braid group is the fundamental group of the regular configuration space, so the ordered configurations. And again, I just wrote these down here so that the betas exist. So those are generated by things called xij. That means one strand goes all the way around, the ith strand goes all the way around the jth strand. And there may be pictures later, I can't exactly remember what those. But the important part about this is a really old result about a fibration. So if we look at configurations of points, I can forget the last point, say the n+1, and this is a locally trivial fibration. And if you compute the long exact sequence in homotopy, you get this reduced split exact sequence here, which tells me that the pure braid group on n+1 strands is isomorphic to a free group with an action by the pure braid group. And we know a lot about this action. In particular, something I want to, and we'll draw more carefully, the free group are going to be generated we call this x1, x2. But we know exactly what the free group generators look like and how the braid group happen. So this is going to come back a bunch as an interesting action. So we can't put the configuration spaces into an operad because you can't shove a disk into a point. You can make an infinity operad if you really want to, but we're going to approximate configuration spaces with the operad of little disks. At the very end, I have something about framed things, but stick with it. Right, and as you saw this morning, so right, these are points in this space, D2n, are embeddings given just by translation dilation, moving. And composition is given by then shrinking this disk, gluing it to the boundary of this disk, and then erasing the boundary. And this is an approximation for sort of configurations of a point where if I sort of homotop each disk to a point configuration. So our main character today is the operad of parenthesized braids. So there's lots of ways to define this. I decided to go with, this is the operad in groupoids obtained by applying the fundamental groupoid functor. Right, that links faster than I expected. But like Mike, I'm not sort of used to slides, so this talk might be like really short or really long, and we're gonna see how this goes. There's a board here for backup when I. So this is composed of groupoids P and N. So objects of this groupoid are parenthesized permutations. So this is supposed to capture like nestings of points. So for example, I have 1, 2, 3, or 1, 2, 3, and then 2, 3, 1. These are all objects in PIV3. And morphisms from any word to word prime are elements of the braid group. So in other words, we're saying that morphisms are parenthesized braids. 1, 2. This. Or I might have change of parenthesization happening in here. And one way to think about this is a model for the operad assembled actually out of the fundamental groupoid of the configuration spaces. And if you want to see a little bit more about why this is a good model, there's some recent lecture notes, I think, by Damian Clark and somebody's name who I'm forgetting and hopefully is not in the audience. That the Operad associators from Assoc with you. There's a lot of literature on this. And in particular, though, it's a co-fiber model. So you could have built a model that's sort of like an operad, symmetric operad of fundamental groupoids of the configuration space. But I really want this one where I also have the parenthesization, because this will be important for the algebra. Okay, so what kind of algebra are we going to do? Well, we're going to look at, so today there's a lot of different aspects of this project. There was this long list of co-authors on it because there's sort of 2 projects. So today we're going to talk about the Lie algebra version. So there's a pro-unipotent or rational or sometimes mulsive completion of a group. Okay, so it's constructed as follows. It's a pretty basic. So you take the group algebra, and I'm just going to pick my field to be Q because that's what I need for today, but you can be more general. And this group algebra is in particular a co-commutative Hopf algebra. But I'm going to take the iadic completion. So that means I'm just going to take quotients by the augmentation ideal and then take the limit. So what does this look like? This looks like and then this is a complete Hopf algebra, and I take the group-like elements. So elements of G hat, those are possibly infinite linear combinations of elements in G with coefficients in Q. Right, so you can have power series essentially instead of just so not anything particularly. But here's a good example, and it's one that will be a key thing because we've already talked about the free group. So if I'm going to have the free group generated by x1 xn, then so a pro-unipotent group has an underlying Lie algebra. There's sort of a canonical way to associate a Lie algebra through the lower central series filtration. And in particular, the free Lie algebra on n letters, which I'll write with little x's, if you take them, the associated group is isomorphic to the pro-unipotent completion. So if we're sticking with our theme, I'm going to be talking about how pro-unipotent braid groups act on free Lie algebra configuration space. Okay. Yep.
What do we mean by degree completing?
Oh, so in order for yeah, that's the degree completion of the Lie algebra. So if I want the exponentiation and log to be inverses, this is an infinite dimensional algebra. I have to. That's like a technical thing. So if I want to take the group-like elements of the Hopf algebra and it be equal to x, then I degree complete everywhere. Sorry.
What is degree completion?
So this is a filtered thing. It has a degree, and then you just sort of allow
At infinite sums or
infinite
something?
sums.
Okay.
Yes. Yeah. So, all right. So we can sort of think about, yeah, so that's just so that when I write X, I really mean the group-like elements in the universal enveloping algebra of Leo. And I can go back and forth. Sometimes less adjectives than that. Anyway, so the braid groups, the pure braid groups, they also have an associated Lie algebra. This is called the Drenfeld-Kono Lie algebra, or the Lie algebra of infinitesimal braids, whichever you like. Right, and this is just, this is a freely generated by little symbols that we call Tij. So they are gonna be the image of the generators Xij, of the pure braid group. And modulo the ideal generated by these relations. So this is literally like a linearization of the pure braid relation. And there's this nice theorem by Kono that says, well, actually, right, this is a canonical isomorphism that the Lie algebra, the Drenfeld-Kono Lie algebra is the Lie algebra associated to completing pure braid groups. And in particular, this is what's the important part. This isomorphism that we talked about, the splitting of that long exact sequence in homotopy that comes from our configuration spaces, this induces a corresponding isomorphism of Lie algebra. So Tn plus 1 is the pre-Lie algebra and n letters with an action now of this infinitesimal braid Lie algebra. So, if we thinking about this, so these are sort of like, we're talking about braids, but we've sort of linearized them. A Drenfeld associator is sort of what happens when you look at, so this theorem that I'm about to tell you about, sort of a Drenfeld associator is, let's say, a universal thing that parameterizes braided monoidal structures on categories. One way to describe this, it's, a pair, so a coefficient in Q and an element of this, Drenfeld-Kono Lie algebra on 3 strands, that satisfy some equations. This is the hexagon of braided monoidal categories, but linearized. This is the pentagon of braided monoidal categories, but linearized. And this is just saying that f of x, y, times f of y, x is 1. So it has some kind of symmetry there. And this isomorphism on the last page, here, this one here, if we account for the fact, right, so in my groupoids, PAB, if I take automorphisms of anything, so these are like the fundamental groupoids. So if I look at the automorphism at any object, this is going to be PABN. So here, locally, if I take completion, I'm looking at this side. Now, if I include what it means to change parentheses between words, I arrive at Drenfeld associators. So the theorem, where is that? Where's the reason? So in terms of tensor categories in Phyton, I know a reference in chapter 11 of this book by Prof, and I think there are many other proofs of this theorem. So I wasn't sure where the first one in Operads literature. But there's a one-to-one correspondence between object fixing isomorphisms of Operads. So here I've completed my groupoids, and PACD is sort of a linear version of PAP, and a set of Drenfeld associators. So there are isomorphisms of Operads in groupoids, which you can think of as basically taking this linearization of the fundamental groups of configuration spaces and then adding parentheses. So here's just an application because the theorem at the end is going to be a generalization of this. So we can use Operad, like why would you care that you have, this complicated thing is equivalent to these maps? There are many applications, but one application is quantization. So what does people mean by a quantization problem? Often it means make a symmetric monoidal category into a braided monoidal category, make something commutative into something non-commutative. Right? So if you want to do this, say you want to think about, I have a representations of Lie algebra, you have to first have something that you're going to deform along. So here sigma is my symmetry, like a symmetric monoidal structure. And if I give a little infinitesimal grading on it, so some type of direction, I'm going to deform my symmetric monoidal structure along the lines of. I call it infinitesimally graded monoid. And here I do need to be at least over like some kind of linear category for what I'm saying. You can do this. There are versions of this in work of Bensby and others that do this for EQ operas, but it's a lot harder to explain. So this is just vector spaces, nothing fancy is happening today. Well, then it turns out that PACD, that operad I introduced, I didn't really introduce, well, that's the universal braided or infinitesimally braided monoidal category. And PIB, well, this is aside from being the groupoids of little disks, is also the operad whose algebras are braided monoidal categories. So if I wanted to quantize an infinitesimally braided monoidal category, I just pull back along one of these operad isomorphisms. And you get the formula, the sort of standard formula in work of Drenfield and those for braided monoidal for quantification. Now, again, if you haven't seen this, that's fine. And I couldn't figure out where to attribute this. This is one of those theorems that everybody knows, but I've never actually seen written down. So I'm going to say the word Tamarkin, because that sounds right. But it's probably somewhere in the 90s. This was the thing. But there's a discussion in this big book on homotopy operads in Prof in chapter 10 that you can put this together yourself. Like all the theorems exist, maybe just not stated this way. Yeah.
How do you know that Greenfield associators always exist?
Drenfield proved that. So the set of Drenfield associators is non-empty. That's a really good question. And that's a solution to complicated differential equations. That's a great question. that would be funny otherwise. Okay. Okay. So I want to look at an extension of this problem, which is sort of known. So I want to think a bit about, this was just about the braid groups, but these braid groups have this nice structure that they split, right? We have the inside PBN plus 1, I've got this action on the free Lie algebra. And such a thing is called it's an example of something called a tangential derivation. So if I want to take a derivation of the free Lie algebra, I can pick something that sort of just acts on the generators by conjugation with some Lie word. Or if you want to think about this as it's a basis conjugating automorphism of the group. So these are very specific types of automorphisms. But this is how the pure braid groups are going to act on the free Lie algebra. So we have we understand that that's how they act. And they're one such example. Okay, so I'll write tangential automorphisms are just the exponentiation of this, or basis conjugating automorphism. And we tend to write them just as a tuple, like so F1 acts on X1, F2 acts on X2, and so forth. Although I should say that it took me about 3 years of learning how to read algebra papers to realize this is just a bijection of sets. It's not actually like I kept trying to prove that was a group homomorphism and it is not. So it's in the literature people write it as a tuple, but that is just abuse of notation, algebra style. So, I felt the need to put that on the slide because that is hard. Okay, so I mentioned in the title, this was about Kashiwara-Vergne equations. So, as with Drenfield associated, so the Kashiwara-Vergne conjecture or a KV solution. So the original problem is about finding universal morphisms that universal solutions to the Duflo isomorphism problem. It comes from harmonic analysis, like it's actually a really, the original proof that there is a solution, so it was posed in the sixties, it was solved in 2003 by Alexia Van Mike, and it's like an analysis paper, I cannot read it. And then later they reformulated it as, like noticing that it had something to do with quantization, they reformulated this as a problem in Lie algebra. And they said that, a tangential automorphism. So very simply put, a KV solution is one of these bases conjugating automorphisms of the free Lie algebra on two letters, such that f of e to the x1, e to the x2 fixes becomes e to the x1 plus 2. And then it satisfies this thing that I won't really tell you about, which is called non-commutative divergence. So this is that the Jacobian is some trace. That's a lot harder for me to introduce in this context. Now I mentioned that these were genus 0 versions. So I can in fact do this for any n. I can do x1 to xn. It goes to e to the x1 plus blah, 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 xn, and so forth. And why are they called genus 0? That is because they correspond to, they're in one-to-one correspondence with formality isomorphism for the Goldman-derived Lie algebras of the free loop space on the surface of genus 0, n plus 1 mark points. So for this 2, this would be for the pair of pants. So the free loop space on the pair of pants, you take the Goldman-derived Lie algebra. If you believe that's a real thing, then like and you check formality isomorphisms, then that's what is parameterized by these solutions for a topologist. And in this beautiful paper from 2012, Alexia Van Robertson showed the set of these solutions is non-empty. And in fact, they use the non-emptiness of the set of Drenfeld associators to prove this. So they're sort of, despite feeling like completely different problems, they're very closely related. Conjecturally, they're the same, but nobody knows how to approach that. Well, certainly, well, okay, I certainly don't. I'm gonna go ahead and guess this. Not open problem. All right, so here's an example. This is a really basic example, and this is gonna be the easy one. So I can define an element, so here as a tuple, x2 and x1, which acts on the generators of the free Lie algebra, just by conjugating. So here I'm acting on the generator x1 by bracket with x2, and I'm acting on x2 by bracket with x1. So, yeah, now that it's sort of, it's the image of the braiding actually. And in general, I'm going to write Tij for a derivation that just acts on xi by xj and acts on xj by xi. And it's 0 everywhere else. And then if I look at these elements as derivations, in fact, this is a Lie subalgebra of tangential derivations isomorphic to the Drenfeld-Konel Lie algebra on n letters. So I'm seeing my braid group pop up here. Observing that and sort of in parallel, it's kind of interesting. The 2012 paper was sort of the original construction, but maybe because it was in the annals, it takes a long time. The 2010 paper, which is a follow-up, appeared first. There's a, I don't know what the story is with that. But there's a companion paper, and there was an observation that actually, because of this image of the braid group and the fact that braids act on the free group by conjugation basis elements, that you could, from any Drenfeld associator, and now I'm going to fix mu equal to 1. This is so this is called the coupling constant of the associator. So now we just lose them. Then the tangential automorphism that I can write in this weird form, and this form does come from somewhere, kind of interesting, which I'm going to tell you about today, is the KV solution. So you can in fact directly construct one of these solutions from every Drenfeld associator, but it's not an obvious construction, and it has to do with this. It's a direct consequence of the splitting of your grade groups. So two of the things that we're going to talk about today is that these solutions arise as isomorphisms of a type of Operad module. Unfortunately, I have to use the word Operad later today. And I'm sorry about that. And that these type of KB solutions also cover quantization of braided module categories over braided monoidal, or maybe just module category. There's a lot of adjectives. Okay, so sorry, this is a long slide, but let's just now learn some constructions with operads. So if I take an operad P, a right module, it's just a symmetric sequence with a composition on the right. So that lands here. Okay, and as you'll probably know if you work with operads long enough, right? It's not hard. You can't really make a bi-module. I guess you could, but it doesn't really work the way you think it should. If you wanted to, I would call this a not quite bi-module, but the term is called a P-module operad or P-moperad. This is a notation introduced by Zillbacher, and he's not here, so we can make fun of that. But I don't know a better name, but there must be one. So this is a monoid in the category of right P modules. Okay, and I'll show you on the next example, this is actually a really natural construction when you're looking at modules over a graded ring. But basically what this consists of is, so I take my symmetric sequence M, and it has a multiplication. It's a graded ring. So it's a monoid, and it has a right module structure from the model. Okay, so like I said, this is kind of a natural, and we can come back to this if necessary, but this is probably the easiest example to think about. If you had a graded ring, right, you can always think of it as a module over itself just by shifting, right? And that's exactly what this is. So every operad you could make into an operad. So just by shifting the operad structure. So if I define P1 of K to be PK plus 1, and then I want the P1Ks to assemble into a symmetric sequence, I just restrict this action to those that fix the first coordinate. Okay. Then I have a monoid composition just by composing in the first coordinate. And I have a right module action by composing in any of the other coordinates. So it's sort of like I've painted one of the elements of my, if you think of operad composition as trees, I've decided that this is a special branch. I should have gotten color, but anyway, I've decided the first entry is special and all the rest the operad access form. So this is a good source of these, but there are also some examples in topology, which we'll do next, that are not obvious. I mean, they're not coming from an operad. So this one is the one we'll talk about. Configurations of disks on a circle, or frame configurations on surfaces is sort of how. So if I want to look at the topological space. So now I want to have embeddings on a cylinder. I think having to watch me draw a cylinder should be. So here, I'm now looking at. Now I have configurations of disks on a cylinder. Or in the punctured plane if you want. So I've poked a hole in the plane. And well, that has an action by the little disk operad. I can compose into one of those disks. But it also is a monoid where I just can stack the cylinder on top of itself and rescale. So that's an example of a natural type of operad structure that comes up. I'm the same, like I'm having a hard time with it. Yeah, that comes up in topology that's kind of interesting. And this turns out to be the exact structure that is actually capturing these, Kashiwara-Vergne solutions, or at least the ones that are constructed from gentle associated. So I tried to make a diagram of this for way too many hours yesterday, but you'll have to deal with that too. So if we now we want to pass to the algebraic problem, and I'll mention a bit at the end that the topological problem itself is also really interesting, but we'll take the fundamental groupoids. And so I'm going to call this PAV1. So the Operad obtained from applying the fundamental groupoid functor to these little two disks on a cylinder. So what I'm thinking about here is that I've added a hole. So I'm going to add a strand called 0. So this is going to be frozen. Are there colors? We just have to pretend they're colors. And then I have other braids. So I have things like this, because a point can go around the hole. And I have other braids. And let's say I have parentheses, and my parentheses can encode 0, but the 0 is not going to get permuted. So because the hole is fixed, right? That label is not going anywhere. This is what you would get if you try to, I think it's there. Oops. I have a remark here. This is what you would get if you tried to write down the fundamental groupoid of the ordered configurations in the punctured plane, and then include like nesting. So this is like a cofibrant resolution of ordered configuration, the fundamental groupoid of ordered configurations in the punctured plane. Okay, so and here I'm just saying that, but still now if I take the automorphism group at any particular point, I actually get something that's isomorphic to the pure braid group again, but now one of these strands is special. So this 0, the one that corresponds to the puncture is special. It stays fixed always, and the only thing I can do is stack on top of it, right? I can't compose into it, so I can't like use that as an operad. But as groups, there's an isomorphism of groups to PBN plus 1, because this certainly looks like a pure braid. I've just re-indexed everything. So in groups, this is same. Topologically, this is not the same. And sort of the operatic structure is also not the same. It's been shifted in a fundamental way. The sort of, if you think about the general things, general elements of this, like from W to W prime, are part of something called a mixed braid or braid group with a frozen strand. And those absolutely are not isomorphic to the braid group in 10 plus 1 strand. So at the pure braid level, there's the isomorphism, the braid level, that's not. They're very different also. That's what it's saying. There's this paper by from 2020, it's on the archive by Damian and one of his students, Martin Gonzalez. I think it was from Martin's PhD thesis that shows this is actually the configurations of the punctured plane. And how this is essentially what you would do if you tried to assemble these configurations into an operad. You would end up with this operad structure.
What does cofibrant mean? These are like in groups, or it's a groupoid in groups, right?
So as an operad in groupoids, it would be cofibrant. So an operad in groupoids is cofibrant, or a operad, if you will, if the objects are freely generated. So these are freely generated by a binary tree.
So like the equivalences aren't isomorphisms of groupoids, but rather just like categorical.
Yeah, they're entry-wise equivalences of groupoids,
Okay.
yeah. But they are cofibrant in the sense if you put a model structure on.
Yeah.
I mean that. So you could take homotopy mass. And Okay, so now I'll just tell you what maps between. My counter. Oh, it's such a way I can't see what number I'm on, but. It's something of 24.
It's
Okay.
20.
Probably 20, okay. Okay, so how do we look at, as I said, so associators were isomorphisms between operads. And we want to think about what this would look like. So if I'm taking a map between modules over a ring, right? So if I have an R module M, put that on the correct side, and an S module N, right? Any module map is a map of abelian groups, but relative to a ring homomorphism. And that's the same thing with this structure. So really, if you want to give a pair, if you want to give a map between a right P module M and a right Q module N, you need to give a pair of maps. So F is a map of symmetric sequences, M and N, for our abelian groups. And F prime is a chosen map of operads, right? And that these things have to be, you know, compatible with the action maps. And even though it's not ideal, but right, if I want to do this for these now operads, so F is just also a map of monoids, right? Because M and N, they're symmetric sequences, and they have a multiplication, a graded multiplication. So the diagrams are much uglier, but you can kind of guess what they have to be. Okay, so here's like the first, now we can actually have some theorems. So this is a version of this here. So there's a one-to-one correspondence between KV solutions constructed from Drenfeld associators and object fixing Moffat isomorphisms, KV1 to PACD1. Now PACD1, this is actually just the shifted thing of the linear. So and I think I'll come back to this again, somehow at the linear version of this problem is kind of, I don't want to say the word trivial, but it is, it's just shifted. But the topological part is actually quite unique. So knowing that you're coming from this punctured topological object sort of governs it. And I wanted to say a little bit about how you prove this. Okay, so what is the construction? Because I want to bring it back to that splitting of the fiber sequence. You don't really need to read all of these equations, but there's in this paper by Damian and then sort of Shannon and I do a version of this. You can just classify what maps look like. Okay, so this is mapped out of a module over a ring into maps over a module over a different ring. And we're saying that, in fact, these are tuples. So mu and f, those are going to be a Drenfeld associator. That's going to be the isomorphism between PAV without the one and PACD without the one, right? There's an underlying isomorphism, Drenfeld associator. And then there's some new power series, new word in here, where I have this Drenfeld Connolly algebra. So this is T21. I'll show you what that is in a second. And it satisfies a couple of equations. So the important part is that you can actually see that the underlying operad part, the ring map, the ring isomorphism is a Drenfeld associator. Then there's a map of the module part G, and it satisfies a couple of equations. And just because, so if anyone knows this stuff, this is the pseudo twist or the Drenfeld twist equation, and this is two hexagons stacked next to each other. The linear side is not super exciting. So we think about what that means. So how do we actually show that this gives you KV solutions? It's not direct, like proving that, you know, the equations satisfied by maps between operads are immediately Drenfeld associated. You have to think a bit about what these objects mean and this splitting. It's kind of key. So you have this triple. So I'm gonna fix mu equal to 1. So here F, this is a word in now the punctured 3-strand thing. So this is where the puncture comes in handy. So I have my special strand over here. And then I have the chord diagram sort of version would be something over here. So this is an element in this T3(1), which, as we saw, just algebraically is isomorphic to T4. Or, as we saw from our splitting, it's an action of T3 on V3. And if you compute directly how this element that's now living here in T3 is acting on V3, you get a tangential derivation from a Drenfeld associator. And I say if you compute directly, and I mean, this is in an appendix of Drenfeld's paper, so if you look it up, because it's kind of hard, this part is a little bit difficult. Then you can see this. And similarly, if you take this G, now this is living in one of these on 2 strands. And it's coming from the fact that I can now parameterize a hole. Right? I can change my associativity around this hole, even though it's not a strand in the grade group. So there's this new element here, K01. And algebraically, it looks just like an element in here, V2 with a semi-direct product V2. But if you go through the pain, and it is, I would call it uncomfortable, of computing what this is as a derivation, like under this inclusion that I showed you, that this maps in here. Well, then you actually can just compute, what is it? It's this derivation here. And I don't expect that you would have remembered what that looks like, but this is the formula from Alexia's Enriquez and Straussian. And the way you like simplify this calculation is using these formulas. So the fact that it satisfies this pseudo twist, that it satisfies this, I think it's called an octagon or octahedron or something, equation, that like forces, plus what we know about the way the associator looks in this, how it acts as a derivation. You use all that information and then you sort of spit out that this has to be this tangential derivation acting on the green. And that's a stated solution. So it's not a direct correspondence in the sense that it just sort of like hangs out there. But you can, the map that goes from these isomorphisms to KV solutions is you had the Drenfeld associator that gave me the isomorphism of Operads. When I determine the isomorphism of Operads, I get this thing and I send that. It's not a pretty map, it's a map of sets. And it's there. Okay. So I was gonna what happened? Okay, so again, why would you like to know? So I picked an application of this and two of them. So an algebraic application. So now I can find actually quantization functors that arise from KV solution. So I mean, then technically the Drenfeld associator is still there, right? But this is like a KV solution that gives me that. So PACD, the Operad, that was parameterizing infinitesimally braided monoidal categories. This is a module over it. It's not that fancy what you should expect it to be. It's a module over a monoidal category is another category together with an action map. Okay. That commutes with all the structure of that category. I don't know if this is good notation for the algebra. I did that actually earlier this morning, so. I don't want to show them. And then, PAB1, this parameterizes, module categories over graded monoidal categories. And these things come up from where you see these sort of module categories over graded monoidal categories are in like representations of quantum groups or in some constructions of TQFTs. So if you want to quantize this, I don't know what your hobbies are. It's a problem that people actually care about, but those people are physicists, so. So if you want to pull this back, so I take any algebra here and I pull back along one of these isomorphisms, the G and the F. F is an associator, that's going to quantize the underlying category, as we saw earlier. And G is now this KV solution, and that pulls the module structure back. And if you're interested in, I'm gonna hit 15 minutes exactly. You don't even get to sign. Oh. Yeah. Well, now we got a whole few minutes. That's just kind of weird. All right, so last slide, but it's so extension. So the interesting side of this is, so I mean, I think the algebraic side is quite interesting, but from the point of view of when you're working in this Lie algebra setting or this rational setting, at the level of chord diagrams, this really is just a shifted object, right? So this is a sort of trivial module structure. At the topological side, this module structure is non-trivial. And it's sort of an open question about what is the topological meaning of these Kashiwara-Vergne equations, but that's a different thing. But so if we wanted to think about this more clearly as surfaces, as punctured, so as configurations on surfaces, we need to include some framing data at some point. So do like higher genus versions of this. So you can take the PARB case, so this is ribbon braid. This is the framed, this is like the fundamental groupoid of the framed little discs operad. So that's where your discs are now allowed to be shrunk, slid over, and rotated. So they sort of capture a bit more, you can think about configuration of framed discs in a disc as a surface, like as a genus 0 surface, and you just blow it up. Then you actually have the Dane twist information around the boundaries. So there's a framed version of this. And as operads and monoprads, somehow the framing, these isomorphisms are independent of the framing, which is kind of interesting. But this allows us to set up a few connections, which is that if you want to build configurations, well, okay, the only example I know of a monoprad of configurations on surface is in work of Campos Sidri and Pilbach, which involves frame points on a cylinder that you then glue into a surface. So you make a monoprad with that. And there is such a thing as a higher genus Kashiwara-Vergne solution, which I didn't talk about, but that involves Goldman-Turayev stuff, free space constructions, and they scare me a little. But you can all, if you're local, you can go, Florian Neff is the one who invented these insane things, and he's just down the road in Dublin. So please go bother Florian. And he will tell you that they're also very hard. If you wanted to approach the higher genus case, we'd need to do this with framing. So with Chandon, we've sort of showed that this is all independent of framing. And also this kind of interesting because there's a different topological version of Kashiwara-Vergne related to universal finite type invariance of tangles, PRV. If you take the cyclic model of, well, there's not supposed to be a one there, of the operatic PRV, and then take its prop, that's isomorphic to the category of tangles. This is a way of looking at Kashiwara-Vergne equations on tangles, which I decided not to talk about because I couldn't draw the pictures. But, okay.
Maybe you said it, but, what did you say made it hard for like the bi-module version?
Oh.
You suggested that it was like very difficult.
So, because like operads, so if you wanted to act on an operad by another operad on the left, right, the circle product is very non-commutative. So on the left, it doesn't commute with, right, co-limit. So you can do like a P algebra, like if I wanted to write down a PQ bimodule. Right, so I can write a right module structure on here, like if M is a symmetric sequence. It makes sense to compose with. Something like this, right? But I can't sort of then also. It would be weird to act this way with the operad, so you can map into. Like you can have a P algebra structure in the category of right Q modules. But I don't know how else to, does anyone else know about? There are other constructions of bimodules and operads, but they're not like what we would think of as the algebraic analog. Or at least not what I would think of as algebraic.
Because part of my question is selfish, because operad sounds. Because oprad's like module and operad, right?
Yeah,
So operad.
I can see where you're going with this, but it's, you have to be careful, someone's gonna write that down. Yeah, and I'm gonna have to referee it, and that's gonna get policy.
The conservative option is bimoperad, surely.
Oh, yeah.
Okay, actually, that is in that, if you keep reading in that paper by the author, that is in fact a bimopera, it gets worse. I mean, the result itself is beautiful, but. I really hope he doesn't watch it.
Are there other questions?
You know, KV solution that doesn't run.
No, in fact, nobody knows one. I know there are no examples, so it is a conjecture, it is conjectured in the paper by Alexei Vatrasian that all PV solutions are Dirichlet associated. It's sort of an open problem. I don't know how you would prove it. Like, I guess this sort of module algebra structure is a way to think about it. But yeah, somehow, like if you actually play with the formulas, I have no idea how you could, construct a automorphism of this type that doesn't come from some formula. I don't know. People have, so I believe that there have been some approaches to proving that conjecture by looking for obstruction to quantization problems. I think Pablo Severa and I want to say Pullman, but I don't remember if I'm pronouncing that correctly. So I've thought about that in terms of like quantization problems. There was one of the reasons they associated this with Goldman Tarayev formality was also looking for obstructions, like an obstruction theory to prove that these Kashiwara-Vergne solutions. But there could be some that come from that don't come from it. So, but there doesn't exist an example of that. And depending on which of the authors you ask, they'll tell you it's probably true or probably not true. So, I don't have an instinct on it, to be honest. Algebra is just a lot of adjectives for me. So from this sort of topological structure, I feel that there's something fundamentally different happening with thinking about configuration from the plane. But then if you look, when you linearize, all I've done is shift my layout around. So if you're gonna find an obstruction, it might be more before you take the. Yes. I invite you to let me know.
Not, then we have a coffee break. The next talk will be 3 o'clock, and let's thank Marcy.